Okay. Good. Okay, good morning. So this is part 3 of the lecture series on electroweak interactions and the Higgs boson. I hope you found some interesting things in Professor Hassan's talk this morning. The general message is one actually that's very important to me. The fact that fundamental and applied science have to merge in some way and trade ideas with one another. I guess most of you in this room are interested in theoretical science. But for me, as an elementary particle physicist, my work is on the theory side, but I spend a lot of time interacting with people who are doing much more practical things, because basically to put together theory and experiment, you need those things. So I have some friends at the Fermi National Accelerator Laboratory in the US who spend their time working on the technology of making very smooth and dust impurity-free niobium surfaces. And for those of us who want to see large future accelerators of the kind that I'll talk about in my 4th lecture, you have to master this technology. And to master that technology, you need both the cooking part. You go into the lab, you try random things, and some miracle happens. But also the material science analysis, which comes from understanding what these surfaces are doing at the atomic scale. And there you go back to tools that come from high energy physics, like synchrotrons that produce X-ray beams, and other accelerators that produce things that can actually probe materials at the atomic scale. And then, of course, high energy physics, when they succeed in building a new type of accelerator, they supply a new technology there. So it all kind of comes full circle. And I think, wherever you are engaged in this process, it's better to be engaged than just to say, well, those guys will figure it out and I just do my stuff. That's not the right way to work. So we'll talk about accelerators in the next talk, but of course, in this talk, there's a very important accelerator technology which is involved, which is that of the LHC. So you all know what the LHC is, the Large Hadron Collider. The LHC is based on a ring, actually in the tunnel, the same tunnel as the accelerator LEP that I described in a previous lecture, based on 8 Tesla superconducting magnets, the technology of which really had to be invented to build the LHC. One needed very strong magnetic fields, and so you had to get there. It's also a big user of information technology. And actually, the LHC was really the proving ground for what we now call the cloud. When the LHC data structures were imagined in the late 1990s, clouds did not exist. The first one is the LHC physics grid, which was built in the early 2000s. And now everybody has a cloud, and people think it's trivial. But it sure was not trivial then. And this is a way that kind of fundamental science can also feed back into the practical things that maybe people who are not in our field are more interested in. I think the message is clear. These things are totally interwoven. And the better you understand that, I think the better you can both carry out your own part of the work and also advocate for science in general. Okay, good. Let's get to work now. So in the last lecture, what I described was the problem of electroweak symmetry breaking. We parameterize electroweak symmetry breaking using the standard model, which has a complex doublet of Higgs fields. We postulate a potential by which one of those Higgs fields acquires a non-trivial vacuum expectation value. This breaks the SU2 cross U1 symmetry. It starts the Higgs mechanism working, and then the W and Z bosons get mass. And then from that, the consequences of the Standard Model follow. But in order to try and understand why this occurs, what is really the mechanism of electroweak symmetry breaking? What is really the agent? We somehow have to probe harder. And one task which is available to us to probe that is to study the Higgs boson itself in detail. So in these two lectures this morning, I'm going to talk about that study. So in the first lecture, what I'd like to do is to talk about what we know now about the Higgs boson. To set that up, I need to describe what does the Standard Model say about the Higgs boson. So what are the expectations that we might try to observe and experiment? And then how are we doing so far with the experiments that have been done at the LHC? So let's go. So, good. So first of all, what we should do is discuss what are the couplings of the Higgs boson within the Standard Model. And this is a subject that can get very technical and complicated. You'll see that as we go along. But the basic idea of how the Higgs boson couples to other elementary particles is really very simple. And it's just shown in this formula. So let me take the complex Higgs doublet, phi of x. It has 4 degrees of freedom, but 3 of them are Goldstone bosons. That is to say, 3 of them are the what happens if I take the vacuum expectation value and then just rotate it into the SU2 cross U1 group. So there are 4 degrees of freedom which are spoken for here. 3 of them are contained in this SU2 transformation. And if I make a gauge transformation, I can actually completely eliminate this by a specific choice of gauge called the unitarity gauge. The other degree of freedom is here, and this is the fluctuation of the vacuum expectation value itself, and this h of x is the physical Higgs field. So of these 4 degrees of freedom, 3 of them are actually unphysical, and the other one is physical, but it also plays a simple role. It's just really a shift of V. And so then we can immediately write down the couplings of this field. We write down the Lagrangian of the Standard Model. We put phi equals V. We simplify that model as much as we can. Then we differentiate with respect to V, and those are the couplings of the Higgs boson. Very simple. So V is equal to 250 GeV, as I've said. And then everywhere that V appears in the Standard Model Lagrangian, we just basically replace V by H in linear order, and we come up with interactions. And that then leads to these very simple set of Feynman rules for the coupling of the Higgs boson. So for example, V appears in the formula for the fermion mass. And so MF over V is exactly the strength of the Higgs coupling. V appears in the formula for the W and Z mass squareds, and so we obtain this formula. Similarly for the Z. Actually, V also appears in the formula for the Higgs mass. The Higgs mass in the Standard Model is lambda times V. And well, you have to also look at the effect of V on the potential, but when you work it out, there's a factor of 3 there. So these are pretty simple Feynman rules. And so if you then put them into diagrams, you can calculate all the properties of the Higgs boson as predicted by the Standard Model. This is very important. Within the Standard Model, there's actually no freedom to change the properties of the Higgs. Once we've measured the fermion masses, the W mass, the Z mass, the Higgs mass, everything is determined. And you can make predictions really to arbitrary levels of precision about the properties of the Higgs. Then if you can measure those quantities to high precision, you have the opportunity to test whether the Standard Model is actually correct or whether there are deviations from it. At the end of the last excuse me, at the end of the last lecture, I gave you a long list of alternatives to the standard model description of electroweak symmetry breaking, some of which required crazy modification, extra dimensions and things like this of the Higgs sector. And presumably those will show up in some way as the statement that this set of interactions here is too simple, and the Higgs properties then are modified. So that's an opportunity that we have, and now let's discuss a little about that. So first of all, I guess we ought to set the stage by talking a little, so now the question is, what happens when you take those Feynman rules and you put them into the theory and you compute the consequences? Well, kind of obviously, if you look at these Feynman rules, they depend on masses. And so the masses that are largest will have the largest interactions, and naively you would say that will dominate the mass of the decays of the Higgs boson, and also the production of the Higgs boson. So what you would expect is that if I, for example, take the top quark here, the Higgs would decay mainly into top quarks. W and Z, their masses are also very large, and so a very large fraction of the Higgs decays would be into W and Z. And that's what people expected in the 1980s. But now we know that the mass of the Higgs boson is 125 GeV, which means that the Higgs doesn't have enough energy, rest energy, to decay either to top quarks, to Ws, or to Zs. And so the main decay modes in which the Higgs is very easy to find just can't be there energetically. And in fact, the whole pattern is going to be a lot more complicated. So what we've got to do then is to look at the decays that occur after you eliminate the ones that are supposed to be the largest. And this leads to a very interesting pattern. What it says is that all of the actual decays of the Higgs boson are suppressed in some way. And we'll see them suppressed by all kinds of different factors. If the Higgs decays to bottom or tau fermions, then there's a suppression by, let's say, mb squared over m top squared. So that particular partial width is small by this factor. If the Higgs decays, it can't decay to on-shell W's and Z's, but maybe it can decay if one of the W's and Z's is off-shell. And in that case, you get a suppression of alpha weak. And it turns out that the Higgs can also decay to gluons, but for that, you get a suppression of alpha strong squared. And all of these are small numbers, which means, one, the width of the Higgs is small, the width of the Higgs is small, the decay rate is very slow. And on the other hand, that because these numbers are all about the same order of magnitude, there's going to be a wide variety of ways that the Higgs will decay. You might think that's a bad thing because it's confusing, you have to learn a lot. But actually it's a good thing because it gives us a lot of different opportunities to study the couplings of the Higgs boson. So let's begin with the easiest case, the decay to fermions. Here, it's basically the interaction is just mf over v, psi bar psi. I've written it down this way. There's a little calculation here that you can follow in the notes. The final result is you can eliminate v in terms of mw, and so you get this formula. Alpha weak over times mh, which sets the overall strength of all Higgs decays. And then there's a factor of mf squared over mw. This would be 1 for the top quark, but as I've said, the Higgs can't decay to the top quark. So instead, it's a suppression factor. mb over mw is a factor of, 1 over 20, and then you square that, so 1% of the natural value. For the final leptons, we can just immediately evaluate this. What you get for the Higgs decay to tau plus tau minus is 260 keV. A keV is a really small number for the width of a 100 GeV particle. Remember, the width of the Z is 2 GeV. And so this is more than 3 orders of magnitude smaller. The rate of the Higgs decay to mu plus mu minus is smaller by the square of the masses. So actually, this is a tiny branching ratio of the Higgs, although one actually might be able to observe it at the LHC if you have very good muon tracking. For quarks, the situation is just a little more complicated because there are QCD corrections that are very important that have to be taken into account. First of all, for quarks, quarks don't have a definite unambiguous mass. The mass, quarks are not observable because they're confined into hadrons. The mass parameter of a quark is also not directly observable. In fact, it's defined by convention because the mass of a quark is one of these things that runs according to a renormalization group equation. Now, when the Higgs decays at 125 GeV, what we want is the mass at 125 GeV. And that's a rather different mass, it turns out, from the mass at the mass of the quark, which is the way these things are usually quoted. So if you go to the particle data tables, for example, you'll see the mass of the up quark quoted as maybe 2 or 2.5 MeV, the mass of the down quark at 4 or 5, the mass of the strange quark at about 100, the mass of the charm quark at sometimes somewhere between 1.2 and 1.8, depending on the convention. The bottom quark, we have in our head that it's a 5 GeV object. But actually, when you evaluate the quark masses at 125 GeV, these are the numbers. And they're noticeably smaller than the ones that you have in your mind or in the particle data book. Also, it turns out that there's a large QCD correction, which is given by this factor. So there's a color factor of 3 and an extra 1.24 when you actually put in the numbers. And so when you put in all that stuff, you find that the Higgs to BB bar partial width predicted in the standard model is 2.5 MeV. And this is actually a large fraction, it turns out, of all Higgs decays as predicted in the standard model. So the total width of the Higgs will be about 4 MeV. 4 MeV is a really small number. If you think that you're measuring GeV things with the LHC detectors, maybe you can measure them to 1%. You're not near the capability of seeing a 4 MeV width of a resonance. So this is going to be a problem that one has to deal with in trying to get the absolute values of the Higgs widths. The branching ratios are somewhat easier. I guess I told you that the branching, well, let me just tell you, in the standard model, the branching ratio to BB bar is about 60%. And then you can use these formulae very easily to get the ratios. So all the other branching ratios are something like this. The tau is a very prominent decay. The charm, somewhat less so. Actually, the charm has this color factor of 3. So did you expect that this number is less than that number? That's because of this mass renormalization that I discussed. Strange is at the 10 to the minus 4 level, and again, the muons are at the 10 to the minus 4 level. Okay. Now, the next part gets a little more challenging. If the Higgs were heavy enough to decay to W plus W minus, or ZZ, that would actually rapidly become the dominant decay channel. And the reason for that has to do with some things I told you about yesterday. The Higgs couples to W plus W minus. The W is massive. The Higgs couples to all of the polarization states. But when we have the longitudinal polarization states, then that, as I told you yesterday, is actually a Higgs state. And the Higgs couples more strongly to itself than it couples to the weak interactions. So actually, those longitudinal states are enhanced. And the enhancement is something like this, mh squared over mz squared. In other words, just this factor that we saw last time in the top quark. So if you had a very heavy Higgs, let's say 400 GeV, it would decay to W and Z pairs. We would have this kind of enhancement, which gets squared. It would be a really large enhancement. The Higgs would be very wide. Now that doesn't happen because the Higgs isn't heavy enough to have this energetically allowed. But nevertheless, we can have a process in which one W is off shell. This W, as we'll see, is not quite on shell. So maybe it's best to think of both W's as being off shell. The W's then convert themselves into fermion pairs, and you have a Higgs to 4 fermion decay. Because there's an off-shell nature, you get an extra factor of alpha W over 4 pi. There's also 4-body phase space, which is typically a small number. But on the other hand, this used to be totally dominant. So for the W, the rate is actually somewhat large. It's predicted to be a 22% branching ratio. For the Z, it's surprisingly smaller, almost a factor of 10 smaller. That's really just because the Z has to be further off shell in order to be allowed in the decay. There's some properties of this 4 fermion final state which are quite interesting. Here's the mass distribution. You can see that one W or Z is very close to its mass shell. But if you really look at this carefully, remember the W is a little above 80 GeV, but the peak of this curve is below 80 GeV. The point is that the W that's near on shell cheats a little toward lower mass in order to allow a little more phase space for the guy which is far off shell. And the same is true for the Z. Now, a very interesting property of these decays is that they are fully reconstructible. So whereas it's somewhat difficult to pick bottom quarks out of the hadronic background at the LHC, a 4 muon or 2 electron 2 muon final state is very observable. You measure the energies of all the particles, you add up the 4 vectors, that should peak at the Higgs mass. But you get more. So first of all, the Higgs is in Higgs decays to 4 charged leptons. You would actually see the Higgs as a resonance. But further, you get to measure the decay angles of all of the particles. So this is a little diagram showing that there are actually a lot of these decay angles. You have the Higgs. It's a scalar, so it doesn't much matter which direction it decays. But then you have 2 Z bosons here, one of which is virtual. There's an angle between the 2 decay planes of the Z boson and an opening angle. We saw yesterday in the discussion of the top quark that the opening angle measures the Z polarization, and the angle between the 2 decay planes actually measures the parity of the Higgs boson. Even parity prefers parallel planes. Odd parity would prefer perpendicular planes. So in the standard model, the Higgs is a 0++, a spin 0, even parity particle, a scalar particle. In other models, you could imagine that you could produce a pseudoscalar particle. So we can test that using these angular distributions. And so here are a bunch of possible hypotheses. The standard model would have a hypothesis which is just H coupling to 2 Z's. You could imagine that H couples to a spin 2 combination of 2 Z's like this. This one has odd parity. H could also couple to the Z field strength, and this actually produces a different pattern of interactions. And actually, shortly after the Higgs was discovered, and even with just really a handful of 20, 25 odd decays to 4 leptons, one could make these distributions. So this is now the likelihood for yellow is the standard model hypothesis. Blue is the likelihood function for an alternative hypothesis. And I think this is, it's even hard for me to read it. This is the 0 minus. This one is the one where you have the 2 field strengths. The actual value from the 20 events is this number here. So you can see in most cases, the standard model is very strongly favored. In this case, it's slightly more ambiguous, but with more data, this has now come out that the standard model distribution is strongly favored over the alternative distribution. So we actually know that the Higgs couples in the way predicted by the standard model, rather than through some of these other operators that I've written on this slide. Now finally, there are loop processes that turn out to be quite important. So we saw that all the other decays of the Higgs boson are suppressed, and so therefore, probably even though loop processes are suppressed, maybe they're only suppressed to the same order, and that's what it turns out. A very important one for phenomenology, well actually these are both very important for phenomenology. The Higgs can decay to gluons. Now, at the tree level, that's impossible because the gluon is massless. But it turns out that, I mean, you can just see that the Higgs could turn virtually into a pair of top quarks, which then annihilate into gluons. And actually, the calculation of this diagram is quite interesting. I'll do it for you in the next couple slides. Similarly, the Higgs could turn into a top quark or a W pair, which then decays to photons. And this process turned out to be very important experimentally, because as with the 4-lepton case, the Higgs decay to 2 photons produces 2 reconstructible gamma rays. So you should see the Higgs as a resonance in that channel. Let's now compute this amplitude. Actually, for those of you who like doing Feynman diagrams, it's fun, well, as I say, if you like such things, just to write down this diagram, and there's another one where the gluons cross, and just compute them directly in dimensional regularization. Some funny things happen, and if any of you would like to do it, and you find funny things happening, please come to me and I'll explain to you why. But I'm going to take a shortcut. So what I'd like to do is to calculate this effective operator using some tricks. So this is the Higgs coupling to the 2 gluon field strength. Now, this is a dimension 5 operator, so the coefficient A has the dimensions 1 over mass, or 1 over GeV. And if that operator is induced, then I get this vertex, where K1 and K2 are the momenta of the gluons. Please notice this vertex is gauge invariant. Oh, well, this is a gauge invariant operator. So then I can just plunk that into a diagram and compute the Higgs width into 2 gluons. So the big problem now is, what is this parameter A? So maybe the first question is, what quarks, they have to be quarks because they have to couple to gluons, what quarks actually give the dominant contribution to this diagram? And this is already, I think, kind of surprising. Ordinarily, you would think you have to sum over all the quarks in the loop, up, down, strange, etc. You'd think that the top quark, being the heaviest, would give the smallest contribution. But actually, that's not correct. So let's just go through that argument. If I estimate this diagram, it's got to have a 1 over mass in it. It's got to have an alpha S, obviously, MF, because the top quark here couples to whatever fermion is in the loop. MF over V is the Higgs coupling. And then when you evaluate the diagram by dimensional analysis, there has to be a 1 over M. And M is the momentum that flows through the loop. Now, actually, it's the maximum of the mass of the Higgs, which is actually the momentum flowing through, and 2mf, which is the off-shellness of the intermediate state. There are 2 cases. When 2mf is less than m Higgs, the diagram, this m is then of order m Higgs. But then see what happens. You get a factor of mf over m Higgs, which is a small factor for, let's say, the bottom quark, or even worse, for the up quark. On the other hand, if you have the top quark, you have an m top here, and then the intermediate state is off shell by m top, so you get m top in the denominator. Now it's cool. The m tops cancel, and you get a result which is independent of the top mass, no matter how large the top mass is. So this diagram, paradoxically, it's dominated by those quarks that the Higgs is not heavy enough to decay to. If there were more heavy quarks, let's say a fourth generation, each member would contribute equally, and so this diagram would be 3 times larger. When you square it, the rate of the process would be 9 times larger, and that's completely excluded by experiment. So actually, this is the best argument that there is no fourth generation. The top quark is the last quark that we will find. Okay, now we can just continue. So now what I've got to do is to calculate the actual value of the loop. And the simplest way to do that is to think about the Higgs as not it being m Higgs. Remember, the top quark is now heavy. So the top quark is dominating the momentum structure of the loop. Let's make the approximation that we bring the Higgs down to 0 mass. So then this is just an insertion of the vacuum expectation value. And so we can write that diagram as the derivative with respect to the vacuum expectation value of the vacuum bubble, this diagram, d by dv, of just the vacuum bubble with top quarks and gluons. Okay, well that's just vacuum polarization. You open up chapter 7 of my book, and there's the formula. So you write it down, you put in the QCD things, and you arrive at this expression. It's gauge invariant. It involves the color factor, alpha s, and there's a 3 pi, which is the subject of a several-page calculation in my book. And then you get the log of lambda squared over mt squared. It's a divergent diagram, so there's a cutoff. However, when we differentiate with respect to v, what it hits is the mt squared here, so the diagram becomes finite, and you get this finite answer, which, as I said, is independent of the mass of the top quark. And comparing to our previous expression, we now know the value of A in the limit that the Higgs is much lighter than the top quark, which turns out to be, it's an approximation good to about 10%. I think, well, here's the full formula, so you can compare them. Okay, as I said, an interesting feature, well, okay, so then there's a small correction from the bottom quark. If you really want to be accurate, you can put that in. But basically now we have the systematics that the suppression is only by alpha s. And so this brings it down to the level of the other leading Higgs decays. Now, an interesting feature of this argument is that the Higgs coupling at the top comes from this diagram, which is the same one that is the top contribution to the QCD beta function. And so you might guess that that's also true for the other decay that I'm interested in here, the Higgs to gamma gamma. And so if you take that seriously, you would then write down this formula, where it's all the same stuff. I removed the color factor. I included a factor of alpha, because this is now an electromagnetic interaction. I look at the contributions to the QED beta function, which come from W and top. And you have to remember to include the Goldstone boson, which gives mass to the W. So you get these factors. And then you get this as the final answer for this loop amplitude. And then finally, you come to this expression here for the Higgs to gamma gamma width. Again, in the limit where the Higgs is much lighter than either 2mw or 2mt. And that, again, it's not perfect, but it's not a bad approximation. And so you can estimate this rate based on this rather simple argument. In any case, if you evaluate carefully, including QCD corrections to the gluon width, you come to these branching ratios. Namely, Higgs to glue is about 9%, and Higgs to gamma gamma is at the 10 to the minus 3 level. Okay, so now we've discussed all the leading types of Higgs decays in the Standard Model. The decay directly to fermions, dominated by B and top. the decay to off-shell WW and ZZ, the decays through loops. Now we can put everything together and get the decay pattern of the Higgs boson. And when you do that, you come to this diagram. Now, the red line is the measured value of the Higgs mass at 125 GeV, and that's what I've quoted all the numbers for. So again, BB bar is more than half, WW is 22%, then glue, tau, and charm at about the same level. The Z is also at that level, 2.7%, I think. Down at the 10 to the minus 3 level, gamma, gamma, and ZZ. Near the 10 to the minus 4 level, mu plus, mu minus. Other things like the decay, direct decay to electrons are orders of magnitude smaller. Now that we know that the Higgs mass is 125 GeV, maybe you could say this is all that's relevant. But actually, the physics that I've described actually qualitatively explains all of the dependence on the Higgs mass within the Standard Model. And I think those of you who want to study particle physics should probably really spend a lot of time looking at this diagram and seeing if you understand all its features. And in particular, why at 170 GeV is the branching ratio to WW almost 100%. So if you think you're a particle physicist, you should be able to answer that question. So I'll take the answers later. Okay. So now with this introduction, we can now talk about the study of the Higgs boson at the LHC. And so now I've told you how the Higgs decays, but of course by reversing those interactions, we can then talk about how the Higgs is produced at the LHC. In discussing the production, I'm going to talk about the parton model of the proton. So the quarks and gluons appear as subconstituents, partons of the proton. You're going to get a long set of lectures by Amanda Cooper-Sarker later in this talk about the parton model and why it's true and how we evaluate, for example, how much energy a typical gluon has within the proton. So let me just assume you know that, and I'll just talk about these processes. So by reversing the Higgs to glue, we get the gluon fusion mechanism. Two gluons come together, resonantly produce a Higgs. The gluon decay is suppressed, but the gluons in the proton are enhanced. I mean, at the LHC, basically, a proton is a flashlight for gluons, and that's almost all it is. And so this process turns out to be enormously larger than all of the other ones that I will discuss. Another process is vector boson fusion, namely two quarks come together, they emit W or Z bosons, those fuse into a Higgs through the direct vertex. Another process is called Higgs-Strahlung. QQ bar annihilate into a Z or W, which then emits a Higgs. This is off-shell, this one is on-shell. So that's an interesting process because you can use the recoil vector boson to tag the Higgs events, which turns out to be very important. And finally, the associated production with top. So if I produce TT bar here, that TT bar line can radiate a Higgs boson. And by observing this process, I can measure the top coupling to the Higgs coupling to top directly. I think the cross sections are on the next slide. So you see they vary over about an order of magnitude, totally dominated by the gluon, but the gluons just produce some kind of very generic Higgs bosons in the central region of the detector. This thing here is the vector boson fusion process. So those produce the Higgs tagged with a certain kinematic distribution. Here are the Higgs-Strahlung processes. And finally here, actually 2 orders of magnitude smaller, is the PP bar to TT bar H. Okay. So, and these reactions have different advantages. For the gluon-gluon fusion, it has the highest cross-section, so we have access to the rarest decays. And that's going to be very important when we look for Higgs to gamma gamma, which is a 10 to the minus 3 branching ratio. The W fusion gives you tagged Higgs decays. And actually, interestingly, it has the smallest theoretical error on the production cross-section. Higgs-Strömlung, again, gives you tagged Higgs decays. And actually, if you think about boosted Higgs-Strömlung, that is the Higgs-Strömlung process where both the W and the B are very boosted, that turned out to be the optimal region for observing the B decay. And finally, the associated production of top, obviously, is how you measure the top coupling. So now we should ask how to discover the Higgs boson at the LHC. So in general, as we'll see, the observation of these processes at the LHC is quite complicated. Maybe we should just go back to these diagrams. So, for example, let's say we're looking for the process Higgs to BB bar. So then the largest cross-section comes from this process where the Higgs then just decays to BB bar. So it's a process where you have two gluons, there's a resonance, and then you get two bottom tag jets. But the rate is very small. It's picobarns. The rate for two gluons to come together and make BB bar jets at 100 GeV in the center of mass is microbarns. It's many orders of magnitude. It's actually 1,000,000 times larger. And under that background, because your mass resolution for jets is not so great, there's no chance to see the resonance. So you need to go to another mode. The one that I said actually worked best is the Higgs-Strömlung mode, where first of all you look for this vector boson, a W or a Z, that then tags the event as having a higher probability of containing Higgs, and then you can go after what's in this final state here. It very much helps to know what the mass of the Higgs is, and until you've discovered the Higgs, you don't know what its mass is. So for that, it really helps to have a mode where you can actually reconstruct the Higgs and find a resonance. And of the modes that I listed, there are only two with that property, namely Higgs to gamma gamma, and Higgs to ZZ going to 4 charged leptons. Unfortunately, this is a 10 to the minus 3 branching ratio, and this is a 10 to the minus 4 branching ratio. With a production cross-section of about 20 picobarns, which was true in the first stage of the LHC, these processes have rates which are 10 to the minus 12 and 10 to the minus 14 of the PP total cross-section. So you need a lot of luminosity. You have to be very sure that you're capturing rare events. It's technically a large undertaking to be able to capture events of this kind and then do that systematically and see whether there is a resonance in those channels. So however that was done, here is the CMS spectrum of 2 photons. Some cuts are applied to this. Another way to get 2 photons is that you can just produce 2 pi zeros. Pi zero decays to 2 photons, but sometimes the photons merge and look like single photons. And that's a much, much larger background. But the electromagnetic detectors of ATLAS and CMS can look for evidence that this merging has occurred and derate the events for which that's likely. And after you've done that, you get this background, which is still due to pi 0, but it turns out there is a noticeable signal on top of that. Or when you subtract the background, which is smooth, you see this resonance at 125 GeV. At the same time, you can look for the 4 lepton final state. Now, this is much rarer. As you see, there are only about 25 events in that red region. But nevertheless, the background is very small, so it just stands out at you. And the resonance is in the same place. So on the basis of these 2 observations put together, you can claim that you have observed a Higgs-like resonance at 125 GeV with high significance. Oh, I didn't put event displays here, but that's okay. Now, once you're convinced that the Higgs is at 125 GeV, you can then use that information to look for other decay channels. An interesting one is the decay to W off shell, which would then give you 2 visible and 2 invisible leptons. Now, you have to think about this hard, because this process is not obviously distinguishable from this process where you just make 2 on-shell Ws, which then decay to lepton, lepton, neutrino, neutrino. Remember, you can't observe the neutrinos. You only observe the leptons. So there are some small differences in the energy and angular distribution of the leptons here, but there's a large overlap of the 2 phase spaces. The signal to background can be enhanced by some angular cuts. It turns out to be a relatively small effect. There's one other thing which you actually have to know about this analysis, which is that if you're looking for L plus L minus nu bar plus jets, actually the dominant reaction that produces that at the LHC is top quark production. Because the top quark decays to a B and a W. The W can decay to L plus L minus. The B is a jet. You don't always recognize that that jet is B tagged. And so you get a large background from that. And so for that reason, this search for the Higgs boson is restricted to events with either 0 or 1, but not more than 1 hard jet. And then some very clever people have to go and compute the probability in QCD that this reaction does not produce 2 or more jets. And actually, there's a whole, at the time when this was relevant, a whole activity to estimate that probability. It's a totally non-trivial calculation. It's not something that's a single order in perturbation theory. You have to resum perturbation theory. In any event, the result of that analysis, or one of the results, is shown here. And the property here that I'd like to emphasize is the following. So this is, please excuse me, muons here, electrons here, 0 jets and 1 jet. And the 2 jet is not here for the reason that I just discussed. The yellow is the background from top. So sometimes when top decays, the bottom quark jet is not energetic enough to be registered as a jet, and then it comes into this sample. A very large fraction of these events are the purple, which is direct WW production. But if you look at this carefully, you see that there's about a 10% excess over the direct W pair production, and that is exactly attributable to the standard model prediction of the signal for Higgs and Higgs to WW. So this is actually, once you get away from the very definitive modes, gamma, gamma, and 4 leptons, this is the more typical situation for Higgs observation at the LHC. That there are many processes that contribute. They're not obviously distinguishable from one another. You just have to observe all of them. You have to understand theoretically what the magnitudes of those cross-sections are, actually to rather high accuracy. And you look for relatively small enhancements, which then you have to prove are both statistically significant and also significant with respect to your understanding of the background. And in this case, one can do that, and so one can claim with this plot the discovery of Higgs decaying to WW. Now, this gets a little more complicated when we consider other factors. Higgs to tau tau. In Higgs to tau tau, actually, it turned out to be most powerful to use the W fusion mechanism as a tag. So let me show you first of all, an event display. So here's an event display for a candidate Higgs to tau tau event. What you see here are 2 forward jets. So the process is quarks come in, they radiate Ws, they then continue to go forward. And so you see a forward jet on each side for the quark that radiated the W. Then here's an electron. You see the a track and an electromagnetic deposition. Here is a muon with, actually it's highly penetrating, and these are some counters which are way out on the outside of the Atlas detector. And so something like this would be a W fusion producing a Higgs, producing tau plus tau minus, in which one tau decays to an electron and the other decays to a muon. So obviously there are lots of backgrounds to processes like this. For example, you can have W fusion production of Z, and Z decays to tau plus tau minus 3.3% of the time, as we discussed in yesterday's lecture. Also, PP to W plus W minus can be accompanied by forward jets. And so you have to think about that as well. Here is the distribution that corresponds to the one that I showed you before. So these are different regions. VBF is vector boson fusion. So if you look at the tight VBF tag in muons and taus, the dominant contribution is this brown tan region, which is actually from the Z. The Higgs signal are these little boxes, white boxes here. And if you look at this carefully, you will see that, in fact, putting this together with other data samples, there is actually a statistically significant signal that those white boxes are actually there. The composite, the most recent composite from CMS looks like this. You can see, for example, in these two channels, which are near the Higgs mass, that there is a significant excess over the estimated Z production background. Green here, it says others. It's a great jumble of things. QCD, various QCD processes that fake this signature. Very often, when people present seminars, they'll just show you this inset, which makes it look like it's totally obvious that there's a Higgs boson there. But you have to understand what's behind that, I think. So this is the background subtracted version of this plot. Okay. The most challenging of the major modes is actually the one which is more than 50% of all Higgs decays, which is Higgs to BB bar. As I told you already, observing glue to Higgs to BB bar is absolutely hopeless. The background is 1,000,000 times the signal. The signal is resonant, but it's not a really narrow resonance. So there's not much hope that you can pick it out. The current analyses use associated production, Higgs-Strelung with W or Z, and that would be a process like this. However, there are important background processes that you also have to take into account, actually with larger cross-sections. One is that you can have a W branching to ZZ. And so an off-shell W can go to ZZ, and so you can get a Z going to BB bar. We saw that BB bar is actually a 15% branching mode of the Z, so there are actually a lot of these events. Also, when PP bar goes to a W or Z boson, it can radiate a gluon, and then through QCD, the gluon can then turn into a BB bar pair. And so that produces something which exactly mimics the signal. Again, it's non-resonant, but you still have to worry about it. Now, the experimenters have used all kinds of interesting tools in order to distinguish these processes. One which is very interesting is that here, notice that the BB bar is a color octet system. Here, the Higgs is a color singlet system. And so you can actually distinguish these processes by measures of color flow. That is to say, the broadness of the hadron distribution that comes from the putative Higgs. And so using kind of clever ideas like that, which work especially well in this boosted region, it's possible to dig this out of the background of these and other standard model processes. I'll show you. Here we go. So again, this is the, when you see people give talks on this, this is what you see. This is the final ATLAS and CMS discovery plots for the Higgs to BB bar distribution. The gray is the Z to BB bar. The red is the excess at higher mass, which is Higgs to BB bar. And you can see that there's a statistically significant signal that justifies the existence of the red boxes. If you dig back in the paper, you see things like this. So this is it's something you really have to think about to evaluate these observations. These are various kinematic regions of that search. The label here says BDT output. So you're using a machine learning classifier to classify Higgs-like events versus background-like events. Please notice the many orders of magnitude on this logarithmic scale. The Higgs signal is enhanced in the Higgs-like events. And you see that in the last couple bins here, there's a significant excess over the backgrounds. However, the backgrounds are extremely large. Top contributes W, Z, many different standard model processes. And depending on how many leptons in the final, or how many B tags in the final state, different mixtures of processes occur. Although rather consistently, in the most signal-like bins, there are significant excesses in all of these plots. And I think this is what happens when you put all of that together. So once again, the signal over background is something that comes out of a machine learning classifier. You see contributions from W, Z plus jets. I'm not sure where the gluon plus jets is here. And the red here would be the contribution of the standard model Higgs boson. Okay. Finally, the LHC experiments have observed the Higgs boson coupling to the top quark by observing the reaction PP to TT bar plus H using basically as many of the decay modes of H as you can try and observe in this context. So you find some top quarks, you look for other things in the event, and the things you can look for are the signals that we've just described. The Higgs to WW, Higgs to ZZ, the gamma gamma, the taus, the Bs. Now, please look at this. 0 is no Higgs. 1 is the standard model prediction. In any given channel, the statistical errors are large. You have to assemble the results of many channels to claim that 1 is allowed and 0 is excluded. Some of the signals are quite robust. Here's the diphoton mass distribution in the ATLAS analysis of TT bar plus Higgs. And you can see that there is a significant bump in the right place. For some of the others, maybe the signal is not so outstanding, but nevertheless, it's there. Okay. Well, this is a lot of hard work on the basis of on the part of the experiments, but now I think we have a great deal of confidence that this object at 125 GeV, number one, really is the Higgs boson, and number two, to a certain accuracy, obeys the properties predicted for the Higgs boson in the standard model. And so here is a summary recently published by CMS. I'm sorry, the top is not on here. But again, 0 is no Higgs. 1 is the standard model prediction. The errors are 20 or 30%. Mu is basically the detected signal rate divided by the standard model prediction. So mu equals 1 is the standard model prediction. And as you see, for many different final states, gamma, Z, W, tau, and B, we're pretty much right on with what the standard model would predict. So the Higgs is, so far, looking very much like the Higgs of the standard model predictions that I explained to you at the beginning of the lecture. Okay. So apparently, the LHC measurements on the Higgs boson are in excellent agreement with standard model theory. Now the question is, what did we learn? And that question will be answered in the next lecture. Thank you very much. Okay. Questions? Yes.
On the previous slide, it seems there's a bias, towards right. The actual measurements, parameter values with respect to
Yes.
standard model.
Yeah.
None of them is towards left. Is there a physics behind this, and why is this bias towards?
When you're talking about discovery, very often there's a bias toward higher values, because if you get a higher value, your significance is larger and you publish. And if the value is lower, the significance is smaller and you don't publish. So it's always true in particle physics. The first discovery always gives a larger rate than the actual rate that you settle down to after you accumulate large statistics. So I don't know, we don't know yet whether that's a factor here or whether actually there is an anomaly which is of order 10%.
What does actually, there is some difference, for instance, in certain cases we have the parameter value around 1.3 or so,
Yeah.
What does physically really correspond to, how much deviation?
Well, this is in the rate. So a deviation of 1.3 in the rate is 1.15 in the Higgs coupling. So then the question is that a big deviation or a small deviation? So in the next lecture, I'll try and answer that question. Okay. But yeah, I mean, this is perfectly consistent with the usual statistics of new particle discovery. Other questions? Yes?
Why we can't see W boson this side of the one?
I'm sorry?
When parameter value was less than 1, why W boson?
Why is this too high? High, you mean? I don't know. This is the data, okay? I mean, you have to remember when you have statistical errors, it never lines up exactly at 1 with the statistics even on each side. I mean, they're always, as I showed you yesterday in the Precision Electra Week, there was a 3 sigma deviation. And I said in a list that long, there's always going to be a 3 sigma deviation. So that's something you have to think about. In a list this long, there's always going to be a more than 1 sigma deviation. Now, why they're all on one side, that's a legitimate question. Maybe that's an indication that there really is an anomaly that we'll see at a higher level of statistics. Yes?
Is there any way to fit anything other than the Higgs in these measurements?
What do you mean other than the Higgs?
Because so far you've shown that it's consistent with the standard model. So
Yes.
It seems like there's no problems.
Yes? Oh, wait for the next lecture. Okay. Does anyone have the answer to the question that I asked? If the Higgs has had a mass of 170 GeV instead of 125 GeV, then the standard model predicts that almost 100% of the branching of the decays would be to W plus W minus. So let me put that slide up again. Does anyone have the answer to that question now? Well, that's part of it, yeah. Are you happy with the fact that the Z branching ratio dips in that region? That's the really odd feature. And the answer to that question is actually you should be okay with that. Because the Z partial width is smooth through that region. But the W partial width is dramatically increasing when you cross the threshold. And then when you cross the Z threshold at 180, it comes back. And the asymptotic ratio is 2 to 1. Okay. There's a lot of other cool physics in this plot, so I encourage you to think about it. Other questions? Yes? Yes.
Is this cutoff tell us that the maximum mass that we
No, the cutoff is because this diagram here is log divergent, right? This diagram has the value alpha s over 3 pi times some momentum factors times a log divergent factor. And because it's top quarks, the infrared is controlled by the top quark. So it's just the usual logarithmic divergence of the vacuum polarization diagram. Okay, now, when you differentiate with respect to V, what you get is MT is equal to MT is the top quark Yukawa coupling times V over 2, right? But the log of MT, d by dV, is equal to 1. Okay, so everything goes away when you actually compute the thing you want to compute. Okay. Yes? Someone out there. Someone had a question. Go ahead.
What's about the concordance of the data from CMS and Atlas?
Yes.
Shown in that plot deviation standard model with respect to, I think, CMS.
Yes.
Plots, right? Atlas also, they have similar?
Yes, they have a similar table. In all cases, I think there are no, I mean, you know, if you really get into the details, you can say, well, Atlas did this first or CMS did that first. But the current state is that the two sets of results are very comparable. And in general, in this talk, I've just picked the one that had the better graphics for the purpose of pedagogy.
Bias towards the right side?
Atlas, I think it's, if I remember correctly, it's less. We can try and look that up.
Still towards the right side.
Sorry, no, it's, so the Atlas is, let's see, I don't know. Let's go back to this. Oh, sorry. So for the tau, I do remember. The tau, the central value is bang on to 1 in CMS. And in Atlas, it's more like 1.5. But I think some of the others, the Atlas is smaller. I think for WW, the Atlas is over here. So.
If they are similar, that may indicate some other physics.
Sorry?
If they are similar, that may indicate some other physics.
Absolutely. Although, you know, as I say, frankly, it's not the time to get excited about that because everything is really consistent within statistics with the standard model. For a while, the value of the top quark was around 2. But it was 2 plus or minus 2. Okay. So what can you say about that? Now the top quark it's still high. It's about 1.5. But again, consistent with 1. Okay. Very good. Let's take a break and come back here and we'll do the last lecture.